Good evening, everybody, and welcome to this inaugural lecture of Bill Gillin's. I'm Bill Spence. I'm the Vice Principal for Research, and I'm really delighted to be introducing Bill here this evening. Bill's been here since 1996, joining the Department of Physics, what is now the School of Physics and Astronomy. I got to know Bill very well when I was head of department there for 3 years from 2009, and Bill played a really crucial leadership role in the department at that time, and he still does. And his contributions led to a major expansion of physics and astronomy and condensed matter in particular. And the whole school's been benefiting from his contributions then and since. I'll say a bit more about his career shortly, but I wanted to say something first about his vision and initiative. An outstanding example of this is the Joint Materials Institute in Sichuan that Bill has organised on organic and carbon-based materials. I remember Bill telling me about his ideas for this lab in China a few years ago. You should always be very positive when people tell you about their ideas for the big ideas, even if you're thinking, wow, that's a really crazy idea, how on earth is that going to happen? In Bill's case, I was thinking while he was telling me this, wow, that's a really crazy idea, how on earth is that going to happen? But at the same time, I was thinking, well, if anyone can do it, Bill can. And in fact, he has done it. And he's done it with a combination of drive and enthusiasm, which has managed to extract more than £1 million out of Sichuan University, and also some money from us as well. So he's done well to persuade both sides on that. Coming back to his career, Bill was always interested in both technology and the physics behind it. He did his first degree in electronic engineering and physics at Loughborough University of Technology. He then took a research assistant position at the University of Surrey, and he went on to work on research projects involving the electrical and optical properties of a wide range of semiconductors. An increasing focus of his research interest was on materials, with applications as infrared emitters for telecommunications applications. Whilst at Surrey, he did his PhD part-time, and this was awarded in 1991 for his work on diffusion in semiconductor heterostructures. Excuse me for reading this out, because I can't remember all these words. Fortunately for us, in 1996, Bill came to Queen Mary and decided to focus on the emerging field of organic semiconductors. And in the last 20 years, he's built up the research group here to become a world-leading centre in organic spintronics and, more recently, organic photonics. In a further recognition of his capabilities, this year Bill was appointed as the Director of the Materials Research Institute at Queen Mary, which has over 50 members of academic staff from physics, chemistry, material sciences and dentistry. The Materials Research Institute is a vital part of our overall research strategy to grow our research base in rapidly developing interdisciplinary areas, so it's very important to us. I could say a lot more about Bill, but that's enough from me. It's time for something from him, Bill Gillin on materials miracles.
Thank you, Bill. Thank you, everybody, for coming. It's nice to see so many friends and family here, as well as many of my colleagues. It's an interesting thing giving an inaugural lecture, because my job is to try and explain what it is I've been doing for the last 30 years to a group of people, and with respect to my colleagues, primarily people who don't know anything about what it is I've been doing for the last 30 years, but have always been wondering what it is I'm doing at university and probably having a good time, because most of them actually knew me from when I was an undergraduate. Undergraduate stroke PhD student. So what I've thought about doing is give an explanation of the research I've been doing and put it into some context that I hope you understand. And what I decided on was this, the mobile phone, or in more detail, the smartphone. So it's something that a lot of us have, and we all just accept it as, well, this is the latest thing, it's just come out, it does all these cool things, so what? And people don't know, care, and they don't need to know or care how it works. So what I want to do is basically try and give you some idea of the materials I've been working on and how they apply to this particular piece of technology. And at the end, give some idea of where this might lead to in the future. Although, And this is something that the government keeps on telling us we have to do. We have to talk about impact. We have to say where our research is going to be in 5, 10, 15, 30, 50 years' time. And what I want to get across during this talk is that although I've been working on these materials for the last 30 years, if you had shown me this 30 years ago, I wouldn't have had the slightest clue about how it works. Despite actually understanding an awful lot of the technology behind it, it would have been a complete mystery to me. And the reason is the materials that have had to be developed didn't exist 30 years ago. So you'd be giving me something and I'd just like, that can't work. Because nobody knew how to make it work. So while I was working on these things, I never had an idea of this was going to be the outcome in 30 years' time, because despite what the government may ask us to do, it's impossible. So we get asked to do this, and every time we put in a grant application, we have to put an impact statement in, 2 pages of A4, where we say, this is what's going to happen. And my belief is that the majority of times, that's complete rubbish. But we all do a very good job of it, and try and get lots of money. So, materials research. So I want to start off, this is a photograph of me in my clean room taken last year. Let's just make sure I get the clicker right first. And for some of my old friends, this is a photograph of me in 1989 in my laboratory. So this is, I've been working at University of Surrey for about 3 years at this point, and I set up this lab and basically sort of got it all working. And for those of my colleagues, many of whom were at Surrey University with me, this was the cloakroom that we used to use when we were going to the student union bar. We'd always stop off in there, drop our coats off, and then go out and have a wild party and pick the coats up on the way back. So this is just to give a context of, being 30 years of research from my PhD to now. So, mobile phones. This is the first mobile phone, commercial mobile phone that was available. Came out in 1983, and it had a 30-minute talk time, which is just as well, because it weighed the best part of a kilogram. And actually holding that up to your ear for 30 minutes would have taken a bit of effort. This is actually Michael Douglas from the film Wall Street. And this scene, I'm sure, was included just to show how rich he was. That phone, at the time, cost about $4,000. In today's money, that's the equivalent to $10,000. And it was a phone. That's all it did. Okay? You could phone people up for 30 minutes. This thing here cost me, just over a year ago, just under £200. It's a phone. It's a high-resolution video camera. It's a GPS device. It allows my esteemed colleagues at front of me to contact me via email any time of day or night, anywhere on the planet, in particular when I'm in China. It has my entire music collection. So again, to those people who've known me for 30 years, that's the best part, 1,000 CDs, all on there. It tracks how much I'm walking. It can monitor my heart rate. There's basically no end of things for this. It tells me when my trains are late. Can't make them run on time, but maybe the next version. So the technology's improved a bit over the last 30 years. So how is it that we've got to this stage from that stage? One of the the universally acclaimed award for cleverness is the Nobel Prize. So one of the first things I did when I was thinking about this talk was thought, okay, let's find out how many Nobel Prizes have gone in to that. There are 5. 5 Nobel Prizes have been required in order to allow me to make a phone call and check if my trains are running. And what's interesting to me is that 4 of those Nobel Prizes have been awarded in the last 15 years. And that gives some idea of the speed with which technology is developing. This is a never-ending progression. And that's why this idea of sort of guessing where our impact will be in the next 50 years never works, because technology is evolving far too fast. So that's the context of what I want to talk about today. So I've been working on materials for the last 30 years, and in particular, I've been working on on semiconductors. And what I want to do in this talk is talk about 4 different types of semiconductors and essentially what role they play, how it is they fit into the phone, and how they've evolved. Now, the first of these is one that I hope all of you will have heard of. Silicon is basically, the main semiconductor. Everyone's heard of the silicon chip. It's the thing that drives all of our technology. So I want to give a little bit of a background on my interaction with silicon. I haven't actually done very much research on silicon, but I have done a bit, and I've published a few papers, so I feel happy talking about it a little bit. Things will go downhill from here. This is the second semiconductor I want to talk about. Now, I imagine that a large number of the people here probably wouldn't even be able to read that. Okay, is that IIIV? What's an II? It's actually Roman numerals. So 3-5 semiconductor. And 3-5 semiconductors are one of the things that actually got me really interested in science and technology back in the 1970s when I was a kid. The third, I think, is called transparent oxide semiconductors, and they're more commonly known as glass. Now again, there might be a few of you here who are starting to think, hang on a second, glass isn't a semiconductor. Glass is an insulator. I remember that at school. I will try and explain why glass can be, and is, in some cases, a very good semiconductor. And the final one are what we call organic semiconductors, or, to the lay audience, plastics. Again, that well-known semiconductor plastic. So, given that I've just mentioned 2 materials that given that I imagine a lot of you probably don't know what a semiconductor is, and I've referred to 2 materials here that you're almost certainly thinking, oh, hang on, I'm lost here. I thought the first thing I wanted to do was say, right, okay, what is a semiconductor? And this is the physics bit, okay? After this, it just becomes stories, but this is the physics bit. So in order to explain what a semiconductor is, I thought, actually, I need to take a step back and explain what an atom is, because this is for a lay audience. So apologies to my physics colleagues here in the front row. So here is an atom. Okay, so this is the sort of thing that I hope you may remember from school. And an atom consists of a nucleus and electrons travelling around that nucleus. This is an atom of hydrogen, so it only has 1 electron. And these electrons, as I say, travel around in orbits just like planets around the sun. That's sort of the school level understanding. And different atoms, different elements, have essentially different numbers of electrons. So here is another atom. This is actually silicon. And you can see that I've drawn there, the little red dots on that are the electrons, the black circles are the orbits that those electrons go in. And I've drawn a number of the inner, what we call orbitals, which are full. They've got as many electrons as can fit onto them. But outside that, there are other orbits that those electrons could go into if you gave them enough energy. So, let's see if I can find the laser pointer. So essentially, as you move away from the nucleus going up here, you're increasing energy. So I want to redraw that in a slightly more simple way and basically say, right, each of those orbitals I've just drawn as a straight line, and you're getting more energy going up. The ones in red are full, they're what we call occupied states. The ones in black are empty, they're unoccupied states. So that's what an atom is, okay? As much as I'm going to do about atoms. So what happens if we start to put a number of atoms together and form a solid? Well, in the simplest case, what happens is these orbitals from individual atoms all start to interact with each other and they start to blur together. And we can end up just drawing it like this. We have a number of what we call bands, but the same thing. These ones down here are full, these ones up here are empty. So now I need to explain how this sort of relates to semiconductors. So each of those bands can be imagined as a box. And the electrons can be imagined as marbles. So these boxes down here are full to the brim of marbles. You can shake it and the marbles might rattle about a bit, but no matter how much you shake it or if you were to tilt it, the marbles actually can't roll over each other because the box is completely full of marbles. The boxes up here have got no marbles in at all. So if I were to tilt this, none of those marbles move. That means none of the electrons move, and that means that it doesn't conduct electricity. So that's an insulator. Now the positions of these different energy levels depends on what you make it out of, what atoms you made. So you can get some atoms that when you put them together, they form like this. So now what we've got is essentially these two boxes have joined together. So what we've got is one big box that's half full of marbles. And now if I tilt that box, the marbles at the top here can possibly roll over each other. So you've got marbles moving. Marbles are electrons, you've got electrons moving, that means it conducts electricity. So that's what we call a metal. Okay? So I hope at the very least, those of you who do not come from a scientific background have taken away something about the physics of electron transport. Now what I want to do is just focus on this insulator. Okay, so get rid of the others. And now what I want to do is zoom in just on this bit here. The difference, remember this is energy, the difference in energy between the top of this box that's full and the bottom of that box that's empty. And I want to just ignore everything else. Now, this energy difference, so this is a place where no marbles can exist. Marbles down here, no marbles up here, no marbles allowed to be in there. As I said, that's an insulator. You tip it, nothing happens. But, as I mentioned, different atoms have different energy levels. So what if we could pick some atoms and just put a few in that happen to have energy levels that were just below this empty one, this box? What would happen then? Well, essentially, those electrons could move up from the atoms where they started into this next energy level, and now you've got a box that's got a few marbles in it, so when you tilt it, those marbles can move. So now we've got a conductor, but not a very good conductor. So we've got a semiconductor. So that's the physics thing. That's all you need to know. That's what I've been doing for the last 30 years. I've basically been working out how to put these little things into these materials so that I can put some marbles into a box. So now what I want to do is, having explained so that the whole audience understands fully what a semiconductor is, actually start talking about some of these materials. And the first one I want to talk about, as I said, is silicon. Now, silicon has been used as a semiconductor since the 1940s. And silicon chips, which is a piece of silicon where you put a lot of transistors onto one piece of silicon and connect them all up to make a circuit, have been around since the 1950s. And there's one guy called Gordon Moore who in 1965 published a paper where he noted that the number of transistors that could be put onto one of these silicon chips seemed to be doubling every 2 years. And that became known as Moore's law. Gordon Moore was quite a smart bloke. He actually went on and founded Intel, which I'm sure most of you have heard of, Intel Inside. But here is a demonstration of Moore's law taken from 1971, so 6 years after he proposed it, or he noted that this was happening, up to about 2011. And you can see that as of 2011, a typical, so these names here, don't worry about them, those are the names of microprocessors. Those are the chips inside your computers that do everything. And now we've got levels up in the billions of transistors on a single chip. And to give you an example, the microprocessor in that is up there. The microprocessor in that has got about 1 billion transistors on it. If you then take all the memory chips and everything else, there's countless billions of transistors in there. Now, I quite like this diagram because down there is this one chip, which is called the 6502. The 6502 holds a special place in my heart because that's the microprocessor that I built my first computer out of. And this is not actually my computer, because my computer I threw out about 25 years ago because it was useless. I wish I kept it. But this is a computer that I built, I was just asking my father, I think in about 1979, 1980. And unlike now, when you build a computer, you basically buy a whole load of bits and you just plug them together. Every single one of these chips I had to solder in place with a soldering iron. And I spent about 3 days working non-stop to build that. And then I seem to remember I spent the next 3 to 4 months trying to get it to work and find out where I'd actually soldered 2 pins together that shouldn't have been soldered together. So that's a whole computer there. That's the inside of this. So I sort of compared these, and basically I've worked out that this, my phone, in terms of computing power, the number of sort of calculations it can do per second, is about 25,000 times more powerful than that computer I built when I was about 15. In terms of the memory it has, when I first built this, it had the grand total of 4 kilobytes of memory. Each of those chips there holds 512 bytes of memory. And when I first built it, I had 8 of them. I quickly upgraded it to 8 kilobytes. The microprocessor ran at 1 megahertz. I rather quickly overclocked that, got it running at 2 megahertz. I was very proud of myself. This thing here runs at about 1.6 gigahertz, so 1.4 gigahertz. So it's over 1,000 times faster just in the rate at which the clock goes. So this is an idea of the development that has happened in silicon over the last 30 years. And to my mind, this is something of a miracle. I find this incredible. This computer here was already as powerful, in fact probably slightly more powerful, than the computer that was on the command module of the Apollo spacecraft that went to the moon. This was actually as good as that. My phone is 25,000 times better in terms of raw computing power, and we use it for checking Facebook and stuff. Not quite as noble an aim, but basically, you know, it's an idea of how much things have advanced in a relatively short period of time. So I regard that as a miracle, but of course that was predicted in 1965. We knew this was going to happen. What we didn't know was that it was going to be used for such trivial nonsense as we all use it for. So that's my limit on silicon. I now want to talk about 3-5 semiconductors, and in particular a material called gallium arsenide. And gallium arsenide is the material of the future. I remember this phrase very well because one of the things that got me through my English language O-level was realizing that I didn't have to write stories, imaginative stories. I could actually convert the title and write something more journalistic. So actually in my English language O-level, I wrote an essay about gallium arsenide being the material of the future. I actually wrote about how we'd be making it on space stations. So, well, got a little bit wrong there. But this is one of the things that really excited me. I found this stuff fascinating, and it's something that I desperately wanted to work on. The material of the future. The saying became gallium arsenide material future, and always will be, because that promise never came to fruition. So why was gallium arsenide the material of the future? Well, the reason was the speed with which those marbles could move in those boxes. A marble in gallium arsenide can move about 10 times faster than a marble in silicon, which means that you can make your transistors 10 times faster. So everyone thought, hey, this is a way of making faster, better computers. The problem for gallium arsenide was you could always make silicon transistors 10 times smaller. And according to Moore's law, we've carried on making them 10 times smaller. Gallium arsenide has other problems. It's actually a bit poisonous, a bit of a pig to work with, whereas silicon is just this wonderful material that makes the world go round. So gallium arsenide always became the material of the future. As a replacement for silicon, as a way of making computers, just never happened. But we still use it, and we use it in here. So in order for me to connect to the mobile phone signal, I need a radio frequency transmitter and receiver in there. The front end of that, the bit that does the amplification, has to work far too fast for silicon. So this thing here actually has a tiny little piece of gallium arsenide in it, working at these enormous speeds that's necessary to actually connect to the mobile phone station. And if some of you've got high-end Wi-Fi routers, they may also have a tiny little bit of gallium arsenide in it. You may also have gallium arsenide related materials in LEDs. So in fact, oh good, just checked I've got a red laser pointer. The red laser in here is made out of a material very closely related to gallium arsenide. It's another of these 3-5 semiconductors. So that's gallium arsenide. What about the concept of 3-5 semiconductors in general? This is a picture of what we call the periodic table. It is all the atoms that exist arranged in rows, left to right, going down in order of number of electrons that they have around them. And this is where the 3-5 comes out. These vertical columns are labelled group 3, group 4, group 5, etc. So silicon is in this group 4, and the group 3 includes things like boron, aluminium, gallium, indium. Group 5, nitrogen, phosphorus, arsenic, and antimony. So 3-5 semiconductors can be any combination of one of these and one of those. But actually, you don't need to have what we call a binary. It doesn't need to be one of each. This laser pointer, for example, might include a bit of gallium, a bit of aluminium, a bit of arsenic, and a bit of phosphorus. Okay, so you can mix those together in different combinations. And as we go down there, the atoms get bigger. So we can draw a little diagram. Don't worry about the names. This thing, lattice constant, is basically how big are the atoms, how far apart they are. And this thing here is the band gap, which is what's the distance in energy terms between our box full of marbles and our box without any marbles. And gallium arsenide sits down here, and you can see there's a whole load of these materials. So all these, what we call binary, so gallium arsenide, indium arsenide. So this is, instead of gallium, we've just used indium. And the black lines are what we call alloys. So something in the middle here is a mixture of indium and gallium with arsenic. Something along there is a mixture of gallium and aluminium with antimony. So for my PhD, I started off working mainly with gallium arsenide and indium phosphide and these sorts of materials down here. And back in the 1980s, this was one of the most interesting areas of semiconductor research to be in. And the reason is, down here is what we call the infrared. These materials emit light in the infrared wavelengths. And we wanted lasers that worked in the infrared because infrared light, when you shine it down an optical fibre, travels further than any other wavelength of light. There's actually a little window called 1.5 microns, which corresponds to a material about here, where if you manage to get light into a fibre at that wavelength, it can travel for about 100 kilometres before it's got weak enough that it needs to be regenerated. So there was a lot of interest in trying to make lasers down here, and the reason was we wanted these optical fibres for telecommunications. So every time you make a phone call, be it on a mobile phone or a home phone, every time you use the internet, the information that's being transmitted is travelling down these optical fibres, and it's based on materials down here. Now I've got some colours up here. So these are materials that actually emit light, and they emit light in the visible, so from red up to violet. And one of the Nobel Prizes that was announced, Nobel Prize for Physics in 2014, was for the development of gallium nitride light-emitting diodes. Those are materials that we do not have in this room. These are materials that are transforming the way we do lighting. So in my house, I've basically replaced virtually all of my light bulbs with LED light bulbs, and they use about 10% of the electricity of a standard light bulb. And I did some research, and a typical office building in the UK uses somewhere between 25 to 45% of its electricity usage is on lighting. And if you can reduce that energy usage by 90% just by going to a different type of light bulb, you can save a fortune. You may even save the planet. And that's why these people got the Nobel Prize last year. So, again, those were the materials that I was working on for my PhD, so the first 10 years of my research career. So the next material I wanted to talk about were these transparent oxide semiconductors. And as I said, these are glasses. And the first one I want to talk about is a material called indium tin oxide. And here's my first little demonstration, which I hope works. So, as I said, everyone knows glass doesn't conduct electricity. So here I've got a sheet of glass, and I hope this works. Yeah. Now, this is not a piece of glass with little wires embedded in it. That would be cheating. This is a piece of glass that is coated with a layer of this stuff, indium tin oxide, that is about 100 nanometers thick. And that is 1/10,000th of a millimeter. Okay? So there is a layer of glass on this glass, and the glass is called indium tin oxide, that's a 10,000th of a millimeter thick and allows this stuff to conduct light very efficiently. The second material, this is slightly more problematic, is what's called fluorine doped tin oxide. And there we have a sheet of plastic. Yeah? Flexible, conducting electricity. I've had so much problem with that demonstration. So these are, and this is now getting on to what I regard as some really quite clever stuff. So how does that smartphone screen work? Because what you've got here is there's no buttons. My fingerprint works. I have a screen, and I can just run my finger over it, and things happen. That requires electronics to be built onto the glass of that screen. And in part, that's made out of these materials. There's one other material called indium gallium zinc oxide, which is actually used for making transparent transistors on there. So that screen there probably has at least 10, or probably about 100 million transistors on it, all of which are transparent, and all of which are made out of this thing here. So how does this touchscreen technology work? It relies on a thing called capacitive coupling. Sorry, there's another big word. Okay, Okay? And what I've done here is I've taken a demonstration of a piece of glass and I've put two little electrodes on it that are next to each other. And you can imagine these could be made out of metal. And you put a little pulse in there and you get these lines of electric field and you get a pulse that comes out of there. So what happens if you were to bring a finger close to this? Essentially, you change the distribution of those electric field lines and the size of your voltage pulse decreases. So if you want to make a smartphone, if you want to make something that you can detect wherever your finger is, what you need is a grid of these little electrode plates. And you can put a pulse down the blue ones here, and then depending on where your finger is, you might get a change in the pulse that comes out of one of those red ones. And that allows you to detect where they are. And if I zoom in on that, what we actually need are these things to be crossing over each other. So these have to be made conducting. We need a little bridge there, so there has to be an insulating material and then another layer put over the top. But that has to go onto a screen which has got light emitting diodes behind it. It's got something giving out light. So these have to be made transparent. And that's where these things like the fluorine-doped tin oxide come in. On these phones, you can make arrays of these little contact pads that are completely transparent to light. And this is a photograph I took of the screen of this through a microscope yesterday. I was well prepared for this lecture. And this is zooming in on that. And what I hope you can make out is a whole load of these arrays here. These are actually the light emitting pixels. I'll come back to those in a minute. But they are also the little capacitor plates that are used for the touchscreen. So we've got dual functionality here. And in there you can just about make out a series of vertical lines coming down here, a series of horizontal lines, these curved lines here. All of those are the wires needed to make this phone work. And each of these little things here is going to emit light, and each of those needs about 5 transistors to make it do that job. And in this little black square there is some of this indium gallium zinc oxide stuff, and there are about 20 transistors in there, 5 for each of those, and those 4 together make 1 pixel. And that's what it looks like when you switch it on. So you can see in there, there's an awful lot of complex stuff built onto the screen there, and as you can see these wires on the top of that light emitting pixel. So these are all transparent conductors. Now, indium tin oxide was first discovered in 1954. So you can say, well, it's not terribly new. But it's only been in the last 15, 20 years where it's actually been developed to an extent where you can make these sorts of devices. Because that pixel there is 25 thousandths of a millimeter across. So one of those wires is about 1,000th of a millimeter across. And you've got to pass electricity through there because you've got to basically drive all these little things. So these things here need to be pretty damn good conductors of electricity to do this job. And the indium tin oxide that was, made 60 years ago was a pretty awful conductor. So it's developments in this sort of technology that has allowed this to happen. And that's the sort of thing that, as I said, 30 years ago, I could never have predicted. Although I knew about these materials, I would never have known that you could make them this good. So these transparent semiconductors are vital for making displays. The final thing I want to talk about is actually these bits here that are glowing. So I've sort of said, well, we've got these, we've got the silicon in the device. That does all the hard work, plays your music, stuff like that. We've got the gallium arsenide, that connects you to your base station. We've got these transparent semiconductors that allow you to get electricity into these little plates that allow your touchscreen to work and allow these little pixels to light up. But how do the pixels work? And this brings me on to my final material. organic semiconductors. This is something that, so back in 1994, I'd been working on these 3.5 semiconductors, I'd been doing a little bit of work on silicon, and I went to a conference in San Francisco, a thing called the Materials Research Society, and I was sitting there listening to talks that really hadn't changed much from the last few times I'd been there. And I left one of these, this is an enormous conference, tens of thousands of people go to it, and there's multiple lectures going on at the same time. And the one I was in, I was finding deathly boring. And across the hall was another talk where people were queuing up outside to get into. And it was on these things called organic semiconductors. So I thought, well, I want to find out something about these. So everyone off the coffee break, I went in, nicked somebody's seat, and sat there and tried to learn something about these, and decided there and then that this is actually what I wanted to move on to. So I started a completely different research field, something about which I knew nothing. And the first thing I saw at this conference were things like this. These are organic molecules, and I'm not a chemist, and I was looking at those just thinking, I don't know what's going on here. And I was desperate. This one I remember, I thought that's actually relatively easy, I can draw that. So I drew a little picture of my notebook of this thing. I couldn't really remember this bit, certainly couldn't remember that. And I thought, well, I'll try and get into these when I get back to Surrey. So don't worry about the names. I can't, so we just abbreviate them. This thing we call TPD, this thing we call ALQ. And I give them different colours because this one here happens to emit blue light, this one here happens to emit green light. So I spent another couple of years at Surrey trying to do chemistry, which I was awful at, but I didn't realise how awful I was until I started collaborating with chemists. And then I started realising that actually, whereas I thought I'd been making this, I probably hadn't. I'd made some of that, but I'd made a whole load of other rubbish as well, and the devices I was making were terrible. So again, if you want to get into this field, you've got to collaborate. You've got to find people with real expertise. And one of the best things that happened to me was I think about 15 years ago, where Peter Wyatt, who I hope is in the audience, yes, over there, actually came to my office and said, look, I'm seen some of the stuff you're interested in, I'm a chemist, can we collaborate? And we've worked together for at least the last 15 years, I think, and have done some really, really cool stuff. We've made new materials, and there's some stuff that I haven't really got time today to talk about, but basically some breakthroughs which we hope may be the next series of miracles that will potentially, I could be talking about when I retire in 16 years' time. Not that I'm counting. So, how do you make an LED out of this material? Well, I'm going to do a very quick schematic. So you start off with a piece of glass and a layer of this transparent semiconductor. Has to be transparent because you want the light to come out through the bottom of it. And then we very simply deposit layers onto it, just like that. Okay? We deposit a layer of TPD, we then deposit a layer of ALQ, and then we deposit a metal on the top. Now, these layers here are we call 50 nanometers thick. It works out 1 nanometer is a millionth of a millimeter. 1 nanometer is about the size of a molecule. So this layer here is about 100 molecules thick. Incredibly thin. But then we connect it up to a battery, and it starts glowing. Actually, it starts glowing really well. So you've got this material system where you can just deposit these layers, as I said, just drop them on top, and then you connect the battery up, and the thing starts glowing, emitting light. How do you do that sort of dropping stuff on bit? Well, this is where that first photograph that I showed. As I said, this is me in my clean room, and this piece of stainless steel here is one of our deposition systems. This is what we use for making these materials. And this is the zoomed out view. We've got a large piece of stainless steel. I close the door on that, and I can pump out all the air. So basically, I create a vacuum inside there. And down the bottom, I've got this bit here. These things here are essentially little heaters. There's a metal coil that you pass electricity through, it gets hot. Sitting inside that is a little cup, and we put our organic material into those cups, we heat it up, it evaporates. Up here is a shelf. I put my piece of glass on that shelf. This material evaporates. When it hits my piece of glass, it sticks to it. And just using this thing here, I can actually control the rate at which those molecules stick down to a level where I can deposit a layer that's 1 molecule thick. Well, if I wanted to do it fast, I could do that 1 molecule per second. Normally, I would do it 1 molecule every 10 seconds or so. If I wanted to be really careful, I could do it 1 molecule every 100 seconds. So I've got phenomenal control over the thickness of those layers. Really high precision. And that becomes vital for making good devices. So the device I showed there with these 2 layers, that was a structure that was first built in 1986, and it's about 1% efficient. So 1% of the electricity that goes in is converted to light. This thing here has got these organic light-emitting diodes on its display. It's got 10 million of them in all different colours. And those structures are a lot more complicated. There isn't just 2 layers, there might be 5 to 10 layers in those. Some of them very, very thin. But again, the principle by which you make them is exactly the same. And indeed, this here is a commercial prototype machine. So this is the sort of machine that an industry could use for making devices that are as good as that if they wanted to. Oops, pulled up the calendar. So how do you make different colours? Well, as I said at the beginning, TPD emits blue, ALQ emits green. Another material called iridium PIQ emits red. And here are a series of devices made out of those different materials. A nice blue one there, which I can see. Yep, I think Pratic. I think you made that.
It's Steve.
That's Steve's eye in there. Green and red. And I always feel a little bit, sort of, in a way, a bit stupid showing this picture, because these are devices we make, and we make them for doing research. And my next picture, again, is a zoomed-in version of that, and that's what you do commercially. So what I've done here is try to give you an overview of these 4 different semiconductor materials and something about what I've done in making them and why they're useful to us. And the thing I want to point out in particular is those last 2 materials. Those are the really novel ones. Those are the ones that, that display did not exist 5 years ago. In fact, 5 years ago, there's a lot of people saying it will never exist. And now you can buy it. And they're all very thin. So I said those transparent conductors are about 100 nanometers thick, 100 molecules. These organic materials are about 100 molecules thick. And because they're so thick, and because you can actually deposit them on flexible materials, you can actually do things like this. This is Samsung's latest phone, the S6 Edge. Now, you, like me, may wonder, what's the point of having a screen that curves around? Yeah. I agree that its use is questionable, but you can do it. And this isn't actually made on plastic, this is made on glass, but it's made on a very, very thin sheet of glass that allows you to bend it without it breaking. So here we've got a phone of use for people who want to show that they've got the latest phone. What's happening next? This is an image of, from a commercial display of LG. These are the prototype televisions that they're making. That's a sheet of glass. It's about the thickness of a credit card. And it's got one of these OLED displays. And you can see that it is actually fairly flexible. I love this because the fact that it's just not breaking. Yeah. I imagine if you've got a TV at home and somebody, one of your kids say, tried to bend it, you'd probably no! Now again, whether that's useful or not is a moot point. You may have seen these curved TVs. Again, that's essentially part of the technology. There's actually, I was told a story by a colleague of mine, George, that actually the reason we have these curved TVs is not because they give you a more immersive experience, it's because the people who make the TVs can't make them flat. When you deposit these thin, transparent semiconductors, essentially you have to heat the glass up to quite high temperatures. And then you deposit these materials on, they form a layer on there, and when you cool them down, the glass cools, or the glass contracts at a different rate to the materials you've just put on it. And then what happens is it bends up. And they've had a lot of trouble basically trying to make flat TVs, couldn't do it, so now we have TVs that we all want. We all want curved TVs for a more immersive experience. My prediction is that in a few years' time, we'll all be getting flat TVs. They'll solve this problem, and actually, oh yeah, everyone had curved TVs were so yesterday. Now what we want are flat TVs that you can put on your wall that are only 1 millimeter thick. So, they're flexible, but they're not very flexible. This is a TV, this is much more prototype, that's actually made on this stuff. Yeah. A completely flexible TV. Now again, so what? Why would you want such a thing? But again, if you look at the marketing hype that people like LG are coming out with, their idea is that you can have roll-up TVs. So you might, for example, have your phone, it's nice and small, but you're on the train going home and you actually want to watch the latest episode of X Factor, and you just pull your screen out. You just unroll it. And you just have a nice big screen so you can watch it, and then you roll it back in, put that back in your pocket and carry on going home. So that's one of the possible technologies that's going to come out of this. Another one, which I really quite like because it demonstrates the transparent nature, are transparent TVs. Now I like this demonstration because it's the first use. So people have been talking about transparent TVs for a long time, and I've been saying, who would want a transparent TV? I want to watch what's on TV, not what's behind the TV. And this I like because it is actually a good use of it. Basically a TV screen put in shop windows. So you can actually put what you want behind, but then you can actually play advertisements in front of it. But, in terms of impact statements, if I wanted to work on transparent TVs, and I was going to say, well, actually, we're going to make TVs that you can look through, so you can watch TV and watch what's on behind it at the same time, I imagine I might not, get very far. But we can already make what we call electrochromic displays. A piece of glass where you flick a switch and it goes from transparent to opaque. So you could imagine having one of these on the window of a flat somewhere, and behind it was an electrochromic display, and you no longer have to have your TV taking up wall space, it now takes up window space. And you flick a switch and your window turns onto a TV, nobody outside can see what you're doing, and then you flick it off again, you've got a window. You could also imagine that you could just light up every single pixel, make it white. So you turn your window into a light bulb. So there are possibilities here for how things might evolve. But, given what I said, don't listen to me, because what these will be used for, we really don't know. There are other marketing people out there who are actually an awful lot more clever of thinking of applications that you don't know you really want. But when they invent them, you'll think, wow, how have I lived without that? The final use for these that I want to mention is this. This is Oled lighting. So again, essentially, it's a very big single pixel designed to emit white light. They can be flexible. And here is this is a real product. This is a light that's been invented or been built. These are commercially available. So Philips, you can go onto Philips' website and you can buy OLED lighting panels. I think one of those costs about 150 euros at the moment. They probably have an operating lifetime of 30,000 hours or so, which if you have it on full time, well, yeah, that might give you a couple of years usage out of it. Whereas the LEDs that we use at the moment, they've got operating lifetimes of millions of hours. Essentially, they're going to last for 20, 30 years, we believe. But the point I want to get across here is that there's a whole load of stuff that's going on, made out of materials, and the important thing is, this is stuff that you see every day, and yet is invisible. You see it, you use it, and of course, you don't care about it, because you don't have to. All you want is the next thing. But I hope next time you pick up your phone, you do think, actually, that really is quite clever. Or even, when the next great thing comes out, I hope some of you think, I wonder how that works, and possibly come and say, Bill, could you explain this to me? Anyway, that's all I want to say for this evening. Thank you very much.